Make sure I have audio. Yep, seem to have audio. So see if we can get this train rolling. We are in chapter 21, aren't we? Yeah. We were talking last time about generators and motors and alternators and really cool sports cars. Today I want to talk about transformers as a sort of a segue subject into actual inductors, how they work and use them how they work in a circuit. Who can tell me what mutual induction or mutual inductance is? Anybody? Well, we've kind of skirted around it. We've made a point of stipulating that when a current is flowing in a wire, it produces one magnetic field that exerts a force on a current flowing in another wire. And the current flowing in that other wire, it creates a magnetic field that exerts a force on the first wire. Well, how does it exert that force? By induction. It induces a current in the other wire. 601. We looked at the solenoids and how you take coils of wire and wrap it into a little loop. And how that would then basically become like a bar magnet. It would concentrate the magnetic flux inside the coil. And then, of course, at the ends, it would fringe out and would, so you would have these fringing magnetic fields extending outside the coil as well. And if you have another coil nearby, then those extending magnetic fields are, in fact, if they're changing magnetic fields, if they're increasing or decreasing, then they are going to intersect that adjacent coil, that nearby coil in some way. They're going to induce a current in it, a voltage, an EMF, a voltage in it, and vice versa. And when we design things to actually do this on purpose, they're called transformers. We call them transformers because they can actually take an AC voltage and increase it or decrease it. If you take a transformer that accepts 120 volts input AC and it outputs 240 volts, that's a step-up transformer. If you take a transformer that takes an input of 120 volts and outputs 60 volts, that's a step-down transformer. What you're also going to learn is that those two are the same transformer. It just depends on which coil you hook up to the input and which coil you hook up to the output. Now, that's not to say there may not be certain special case applications for transformers where other design features are added into it that cause you to have to pay attention to, especially when you start getting into things like three-phase and stuff. It all just gets weird. But in its simplest and purest form, a transformer doesn't care. It's not a diode. It doesn't care which way it goes. If you put the voltage in one side, the voltage on the other side will be stepped up. If you turn that same transformer around, it'll be stepped down by the same amount. So let's look at how that works. Let's start with that solenoid that we were talking about. Now we know that if we put now, is this because of the board in this location, or is it because of the markers? I don't know. Anyway, we've got this coil. We run a current through it, and it produces a magnetic field. And there's lots and lots of magnetic flux inside here. But out here, it fringes out like so. Now let's say we take another coil here. Boy, this is... Okay, let me see if this works any better on another board. When these magnetic field lines expand over here, depending on however much flux gets to this coil, it's going to induce a voltage over here. We looked at we mathematically looked at how to calculate the amount of EMF induced in a coil by a magnetic field. What was it? Back up and look. Change in flux divided by change in time. But in this case, we have more than just one strand of wire. We have many loops, right? So, however, this will have to be multiplied by the number of loops of wire that the magnetic field is crossing over. Of course, you can kind of look at this and intuitively tell that this isn't really going to be very efficient, because most of the magnetic field is never going to get over to this coil. So what if we take a kind of an iron core, something with a high permeability, and we run it through this coil and bring it back over here to this coil. Now what happens to all these magnetic field lines? All of these magnetic field lines that were fringing out into the atmosphere are now going to be contained inside that magnetic core up to some point of saturation. Okay? Now, eventually, based on the permeability and the physical size of this metal core, this iron core, at some point, it's going to be saturated, and it will have as much flux in it as it can hold. And any additional flux that's produced by this solenoid would then start leaking out into the atmosphere. But that can be controlled. You can make the iron core bigger. You can make it fatter. You can make it hold more flux, as much as you need. And in fact, we're going to look at the efficiencies of these things. Maybe. Point is, these transformers, by using this technique, they can be made They can, obviously they can never be made 100% efficient. Okay? But they can be made close enough that that the difference doesn't matter. They can be made significantly greater than 99% efficient. Okay? Think about this. What's going to be one of the primary losses due to this transformer? One of the primary loss mechanisms for a transformer is called eddy currents in the core. And you have that core. When you have that core, and you start filling it with all this changing magnetic field, then that changing magnetic field is going to start inducing electric currents in that core. And there is no convenient and easy way to figure out where those currents are going to go. They're going to go in whatever direction produces the least resistance at that moment, based on the direction of the magnetic field and the rest of it. But you can control those eddy currents. How? Anybody? How would you control the eddy currents? Say it out loud. Laminations, yes. If you take that core and instead of just making it a solid piece of metal, you make it into a stack of laminations, then those currents that are induced can no longer flow transversely and start creating stray magnetic fields that run at odds. Obviously, Lenz's law is always going to be a factor, but by putting in these laminations, you can force all of those eddy currents to stay in these two-dimensional planes and minimize their effects, minimize the losses due to them. And like I said, we're not going to go into the math of it, but you can literally make these things much greater than 99% efficient. So for our purposes, doing the math on how to use these transformers, we're just going to assume that they're 100% efficient. In reality, they're never going to be quite there, but you will find that they can get very close. So, okay, cool. And in that other course, I would probably been. Let me ask. Okay. This was over in the power in. Yeah. Yeah. Yeah, and if you're going to get into the nuts and bolts of that, then this would be. Did y'all look at why power line, transmission lines use such high voltages? Yeah, that's basically what we're going to look at here. Have you done have y'all gone through the math of how a transformer works? Step up and step down. Okay, well then let's do it quick then. What is the voltage induced in this coil? What's the voltage in what is the voltage induced in this coil? Going to be the change in flux in that passes through that core, which is contained in the core, per unit time times the number of turns on that side of the coil. Same thing is true over here. If this is 1 and this is 2, then EMF 2 is going to equal the change in flux per change in time, which is the same flux, it's in the same coil, times N2. Why do I get I have the nagging suspicion that I'm skipping something, and I don't want to. Well, the units of EMF are voltages. So we set them. Now we just divide these two equations, take the ratio of the two equations. Change in flux with respect to time goes away, and we end up with N1 divided by N2 is equal to V1 divided by V2. All right? If N1 is smaller than N2, if there's fewer coils on side 1 than there is on side 2, then it goes, depending on which side you hook up as the input, it either steps up or steps down based on the ratio of the coils. Okay? Now, as you probably have already learned from your power distribution class, you don't ever get anything for free. Right? Right? Why is that? But why? What's at play? What is the physics involved here? Conservation of energy. See, the voltage is not constant from one side to the other, neither is the current. But what has to be constant is the power. That's why when you look for transformers, when you look them up in your catalogs and you're trying to order one, how are they specified? They're typically specified as so many volt amps. What's a volt? What is voltage times amperage? Power. So, power does remain constant. Regardless of what happens to the voltage and the current, the power that you put in will be the power you get out times some constant of efficiency, which is can be made very close to 1, so we're just going to pretend like it's 1. But so the voltage times the current in must equal the voltage times the current out. And like you said, if the voltage going in, if the voltage coming out goes up, then the current coming out has to go down so that it remains constant. Now, how would you manipulate these? You own a transformer that you have a voltage 120 volts AC, 60 hertz, and you need 240 volts. Well, your primary voltage is 120, and your secondary voltage you need is 240. Then that gives you the same ratio. You need the same ratio. That's what? 1 over 2. So you need twice. You need an N1 to N2. Would be 1 over 2. So 2 times N1 must equal N2. All very, very straightforward. There is one more thing I want to look at before we move on. and that is transmission lines. They use the example in the book to work through, so everybody get out your calculators. I want us to work through the actual arithmetic here and see what happens. We got a power transmission line that we're going to send. Well, what's the example they use in the book? 120 kilowatts of power. Going to transmit to a small town. And the resistance of the transmission lines themselves, the total resistance of the whole length of the transmission lines, .4 ohms. Is that right? I'm on page 603 now, example 2111. Yeah, 0.4 ohms. Now, how much power, how much would be lost if we transmitted this at 240 volts? And then how much would be lost if we transmitted it at 24,000 volts? Well, how much obviously it depends on how much current's flowing. Right? Well, that means if we're transmitting 120,000 watts at 240 volts, how much current is that? Does that really work out to 500 amps? Someone with a calculator confirm that. Okay. Well, now we can look at how much power is lost with that much current. That's actually dissipated in the actual transmission lines. It's I squared times R. So 500 squared is 2,500? No. 500 squared is what? And multiply that by 0.4, the total resistance of the lines. You lose 100,000 watts wasted in heat, dissipated in those transmission power lines. Now repeat the same problem, but this time take your 120,000 watts and divide it by 24,000 volts. And now your current is what, 5 amps? Now 5 squared now is just 25 times 0.4, which gives us what? 10 watts. So out of 120,000 watts total, you only lose 10 watts in the transmission lines by stepping it up to a high voltage. In fact, those big, giant transmission line towers that you see look like giant scarecrows going out across open plains. Don't they generally run those like 600,000 volts? A lot higher than just 20. I think when they come off of that, they go down to substations. I think they branch off of the high power transmission lines down to like this 24,000, 2,400 something. I don't know. You'd have to ask your professors over at Power Distribution. Y'all may well know better than I do. Do y'all know what these numbers are that they actually use? That's reasonable. And it gets down to a substation level where they bring it down to like 2,400 or so that they actually pipe it around at the street level. Before it gets to the transformer on the pole outside of your house where it's brought down to the 240 volts for your normal mains service into your house. This is why. You're pumping in the same amount of power, you're getting out the same amount of power, but the power that you're transmitting is not the source of the losses. The source of the losses is the heat generated by the current. That's the beauty of a transformer. Crank up the voltage, the current goes way down, but the power across stays the same, or very nearly the same. How many of you are familiar with the whole AC-DC controversy back when Thomas Edison and Nikola Tesla were rivals? You remember what happened? Yeah. Thomas Edison, he wanted the contract to provide power for the cities, the Con Ed, Connecticut Edison Power Plant, whatever. Nikola Tesla was a huge proponent of AC power for these very reasons. He'd done the math and he'd worked it out and wanted to, and was ready to show. It could show that it could be done more efficiently and more economically and more cost effectively by using AC voltage instead of DC voltage. Tom Edison was committed to DC voltage because he felt it was simpler, easier to understand. I don't know. But the one thing I do know is he absolutely did not want Nikola Tesla coming in and stealing his thunder and cutting in on his profits. So he basically went on he launched a character assassination campaign on Nikola Tesla to discredit him. And he even set up a demonstration where he used AC electricity to electrocute and kill an elephant. He did it publicly. He took an elephant, hooked it up to a power mains, turned on the juice, and electrocuted an elephant so he could say, "Look, see how dangerous this AC electricity is?" Say again?
The video is on YouTube.
Well, I don't want to see it. I've seen a man electrocuted in the electric chair. It is not something you ever want to see twice. It is of all the ways we've executed people in this country, it has got to be the most heinous. Anyway. Oh, Edison. It's called Con Edison for a reason. He won. What he didn't do was he never bothered to point out that you could do the same thing with DC electricity. It didn't matter that it was AC or DC. It was, he pumped enough power in to kill an elephant. But he won the argument. Now here's the real irony. Once he won the contracts and started providing power, all of a sudden he decided that maybe all that AC was better for a reason. This is the reason. Because he realized real quick that DC power that he was so fond of was eaten into his profits. And of course, you can't use a transformer with DC power. You can, but it takes a lot. You have to put in like a multi-vibrator. And you basically have to take your DC current, convert it to AC, pump it through a transformer, re-rectify it, and so it becomes a. What happens if you hook up a DC current to a transformer? Over here, we got our transformer. Wrong one. Oops. We got our transformer. There's a graticule of our oscilloscope. Here's our battery. You close the switch. What happens? Voltage on 2 channels. We got our primary channel here. Close the switch. Voltage goes up. Turn the switch off. Voltage goes down. That's on the primary channel. What do we see on the secondary channel? Close the switch. You get a spike where the voltage, while the voltage is changing, you induce a current. Once the voltage stops changing, your induced current goes away. Stays at 0 until you get over here, and when it starts changing in the other direction, you get another spike going the opposite direction. That's what happens if you ever hook up a transformer to a DC supply. You get spikes when you turn it on and spikes when you turn it off. But you don't get actual in order to use the transformer, you have to have an alternating signal. You have to have a time-changing signal. It doesn't have to be a sine wave, but it does have to be changing. Any more questions? Any comments? Oh, while I'm at it, do we have any questions from the homework so far? Past homeworks. Everybody, yeah, go ahead.
I was going to ask about the term, because I know you have to have, like when we were talking about the ratio, like if you needed a 1 or 2 to step it up, what's the difference between doing 10 turns and 20 turns or 100 turns?
It's going to affect the total resistance of the wires that make up the coils. In general, you want lower resistance and for higher inductance, because that determines what's called the Q, or quality of the circuit. No, but it will affect how close to 100% efficient you get. It will affect the efficiency. With any inductor, you're going to have what's called Q. So basically, the lower your resistance. The ideal case would be 0 resistance in your coils, which of course you're never going to get to. This was a question that came up in a homework assignment recently, where you were asked about, if you had a certain amount of copper and you needed to generate as the biggest magnetic field you could, would you be better off using short and fat wires or long and thin wires? And I think I ended up just giving everybody the point for the question, because I don't think anyone got it right. Everybody said you want short and fat. But in fact, what controls, what's the primary thing that, now you're thinking about the length and the diameter of the solenoid, but of the wire, you want the wire to be long and thin so you can get more turns in a shorter space. Now, within the limit of the fact that you're going to make the thinner you make the wire, the resistance is going to go up, and eventually you're going to start burning out the wire before you know, so there's a limitation there. But in general, you would get more magnetic field with more turns in a shorter space and in a smaller diameter. So, anyway, but answering your question, though, the main effect of going with smaller and smaller wires is that you're going to end up, you will start to increase the resistance till it becomes deleterious. And as with most problems you deal with as an engineer, you're always looking at trade-offs. You're looking to optimize based on two or more parameters. In this case, to make that transformer work, you want as much magnetic flux as you can generate. And that means you need more turns to generate more magnetic flux. To induce more current, more flux. But you also have to be aware that if you make the wire too thin, infinitely thin, you're going to start increasing resistance. Of course, before that happens, you're probably going to saturate the core. At which point you've pushed it too far at that point. So to the extent that you can do so without saturating the core, you want to produce as much magnetic flux as you can. And that means more turns. I say more magnetic flux. You're producing more magnetic flux and you're inducing more voltage per amp when you do that. What else? Any other questions? No. We talked about mutual inductance. I'm on chapter 2110 now, page 608. We talked about mutual inductance as a way of getting started on transformers. Now let's talk about self-inductance. What happens when you actually make one of these coils and hook it up into a circuit? What happens when you start putting a current through this coil? As the current starts to increase, the charges start to move. Every one of these little coils starts building up and adding to a magnetic field that becomes a magnetic field, like a bar magnet. We've already looked at Lenz's law. What happens with Lenz's law? The field that the current produces is going to intersect with all of its adjacent wires to induce a countercurrent, a countermagnetic field that will oppose the changing current. Right? Is everyone wrapping their mind around this? Do we need to go through and work through the mechanics of how this happens again with the magnetic field, and how as the current increases, the magnetic field builds up? But when that magnetic field builds up, it also induces a current in the same coil, which will tend to oppose the initial change in current that's causing the magnetic field to build up in the first place. Well, if this is the voltage if this is the voltage that's induced in the coil by itself, and that's equal to the voltage that's being induced, we also know how else do we know to calculate the amount of EMF that's being induced? Well, divide through by -1, we end up with L delta T, delta I delta T is equal to N delta phi delta T. Right? Multiply through by delta T, we end up with L delta I is equal to N delta phi, and so we can write L is equal to N delta phi delta I. Everybody with me so far? Okay. Try to clean this up. N delta phi delta I, change in current. Change in magnetic flux per change in current. All right. But what is this term right here? Delta phi. Remember how we calculate the magnetic flux? Somebody? Mu sub naught, permeability of, in this case, free space. Over length. And this is the length of the solenoid, not the length of the wire. You remember that, right? In this case, we have the solenoid like so. This is L here, not the length of the wire. So, all right. Weber's, either one. So, if that's phi, what would delta phi look like? Changing flux and changing time. U sub naught doesn't change. The number of turns doesn't change. No, not all of it. The area stays the same. The length stays the same. The only thing that changes is the current. So delta phi is just the same phi except with delta I instead of, well, now we plug this into our equation here and we get L is equal to mu sub naught, getting ahead of myself. L is equal to N over delta I times delta phi, which is times mu sub naught N A delta I over L. Our delta i's cancel, and it looks like the n's get squared. So we end up with mu sub naught n squared A over L. That is the self-inductance of your coil, of your solenoid. Now, of course, in this case, we're using mu sub naught. Somebody remind me, what's mu sub naught? Permeability of free space, exactly. Something like that. It's on your index card. Yeah, 4 pi times 10 to the, is it plus 7 or minus 7? Minus 7? Okay. But that's the permeability of free space. In other words, if this coil is an air coil, actually it assumes that the coil is in a vacuum, but it turns out that the permeability of the atmosphere is very nearly equal to the permeability of free space. So again, one of those things that probably not going to be concerned with. But what if you shove a nail through it? And I don't mean like the carpenter, the roofer jammed a nail through your circuit board. I mean, if you actually take a piece of iron and shove it down the core of that, now what permeability do you use? You change permeability, it's no longer mu sub naught, it's mu for whatever metal you're putting into the core. And of course, that assumes that it's still going to assume that you're at not pushing enough current through to saturate the core with, and start pushing fringing flux lines, flux field outside into the atmosphere. What are the units of inductance? They are. Henrys. And they'll probably tell us the guy's name in here somewhere. I don't remember it offhand. It is on page 608? Oh, how could I not remember that name? Joseph Henry, really? Cool. How many of you are familiar with that one? Eli the Iceman. You, any of you? Yeah, no? You are? Tell them. With an inductor, voltage leads current. With a capacitor, current leads voltage. What does that mean? It means when you have a circuit and you've got a capacitor, you first turn on the voltage. You apply a voltage. Current is going to start to flow. And as it flows into and stores into that capacitor, stores a charge in that capacitor, voltage is going to increase. So your current will do this, and your voltage will do that. Current leads voltage with capacitors. With inductors, it's just the opposite. Capacitors want to keep the voltage the same. So you have to pump in charge to change the voltage across a capacitor. Inductors want to keep the current the same. So you have to push a voltage on it to force a change in current. When you first apply a voltage, current starts to flow. But the inductor then induces a magnetic field into itself to oppose the flow of that current. That's Lenz's law. So your voltage has to build up first, and then the current will follow. In this case, you turn on the voltage first, and then the current will follow after it. Eli the Iceman. Inductor, voltage leads current. By how much? We're assuming that you have a sinusoidal voltage signal wave, then this will induce a 90-degree phase shift. That's why when you're writing them and rectangular coordinates, You have, well, I don't want to, we can't get there until we talk about reactants. So, and that's where we're headed, hopefully. That's where we're headed. Yeah, reactants. You've got to, in order to calculate a circuit, you have to have, capacitors are in units of what? Farads. Inductors are in units of henries. Okay, more likely microfarads, millihenries, but picofarads. But there's nowhere in Ohm's law will you find any mention of farads or henries. You need ohms to relate voltage and amps. Now, this is where we're going to get into reactants next time. So we'll pick it up there next time. We'll convert these into reactances and then start using them to calculate currents flowing in circuits.